Hello, welcome back to your Mechanics of Deformable Bodies. So we will now proceed with your Module 5, Stresses in Beams. Okay, so in your Module 4, we discuss about shear and moment equations and diagrams. Okay, and we reflect that one on the actual beams. And then now we will discuss on this specific types of stresses of beams. Okay, so in this unit 1, we will be discussing about flexural stress. So for this unit, these are your desired learning outcomes. So first is to derive the formula for flexural stress, and then to compute for maximum flexural stress present in a beam. Okay, so stresses in beams. Considering this beam, okay, let's say that this is a simply supported beam. Okay, you can read your descriptions here or your explanation here. Okay, let's consider this beam. Okay, and then this beam, okay, let's assume that this is composed of thin fibers, which is parallel through its grain. Okay, parallel to its grain. So let's say again the cross section, if I will cut that beam at a certain section, that is composed of a very thin fibers, okay, which is parallel to the beam axis. So let's try to analyze it that way, and then let's consider that each of that member or each of that fiber will experience different values or different intensities of stresses. Okay, so if we will try now to apply this one, okay, if we will try to apply this loading, and then we will try to get the moment at the section, if we will try to cut that one and take the moment at the section, we will end up with what we call as the internal moments. Okay, and then of course due to the loading and then due to that internal moment, there will be what we call as the deformed shape. That beam will deform. Okay, that beam will deform itself, and then there are two possibilities. There are only two possibilities. We are referring to simple beams and then simple loadings. It's either the beam will curve that way, or it means that if that will curve that way, the upper part of the beam, okay, this is the beam, okay, let's say that this is the beam, the upper part, if that will bend that way, will be under tension, okay, that is obvious. And then if that is under tension, the lower part will be under compression. Imagine a beam, okay, imagine a beam, let's say this is a beam, and then that will bend that way. So the bottom will be compression, the top will be tension, under tension. Okay, and then there is, if this is tension and that is compression, there is that layer somewhere there in between, which is, if you will try to look at our figure here, we call that one the NS, okay, or that is neutral surface. Or if that is now referring to the cross section, if you will try to cut this one and look at the cross section, this surface will intersect the centroid, okay, or this surface will intersect the cut surface, and that will be that will serve as a line, and we call that one the neutral axis if you are looking at the cross section of this beam. So again, the division of the tension fibers, okay, again, as I've said a while ago, let's imagine that this beam is composed of thin fibers, and then some of the fibers below will be under compression, some of the fibers on top will be under tension, and then the somewhere in between, somewhere at the middle of the tension and compression fibers will be a fiber, a surface or a fiber on a surface that is not under any stresses. So it means that that is neutral. There is no stresses at all. It is not under tension, it is not under compression, and then that surface, which is composed of those fibers, which is unstressed fibers, we call that one the neutral surface. Or again, if you will try to cut that one on the cross section, okay, this is the surface. If you are looking at that, if I will cut that one, it will be intersecting your cross section into a line, and that is your neutral axis. And then the other way, okay, the other possibility is if your beam is loaded and that will curve this way, or that will deflect this way. And actually that will be the scenario in this case, wherein your loading is on top, so that will deflect that way. So the top is now the compression, and then the bottom is the tension, because imagine that one, okay, this is originally flat, and then that will bend that way. So of course you will expect that this will be under tension and the top is under compression. And the same thing, you will find there at the middle of the compression fibers and the tension fibers an unstressed surface of fibers, which is what we call the neutral surface. Okay, so by the way, if we will try to relate this one with the discussion of torsion, as I mentioned in the torsion, that torsion is a variable stress. Okay, before on the previous modules we discussed that we assumed that the cross section, if that is under pure tension, pure compression, the section has a uniform stress. And then we discussed also in your torsion that a cross section under torsion has a variable stress, and I explained that one, isn't it? The stress, the shear stress in a torsion, in a member under torsion, the shear stress is increasing as the distance is increasing. Okay, the distance that we are referring is the radial distance, which is from the center. Okay, so that is a variable stress. Same as this bending stress, okay, or flexural stress. We call this one flexural stress or bending stress. If you will try to cut this one at the middle and then try to look at the cross section, the stresses, okay, just for example this one on this upper possibility on the top, okay, the upper is cotension and then the lower is compression. It doesn't mean that on this upper of the neutral surface that is a uniform tensile stress. No, it is also a variable. That's why, as I've said on the torsion, that torsion is the same as flexural stress. It is a variable stress. So as we go away from the neutral surface, this tension will be increasing. Same thing, as we go away from this neutral surface, the compression will be increasing. Compression stress and the tensile stress will be increasing. And then that will be derived later on. The relationship of that, or the formula for that, will be derived later on the succeeding slides. Okay, so that's why this is a variable stress. Unlike in a pure compression and the pure tension members or a pure shear members, that the cross section is experiencing a uniform stress. Okay, so torsion and then bending or flexural stress are variable stresses. So at a certain cross section of a member, these stresses are not uniform or not the same. And just of course, just imagine this one. On the other side is compression, on the other side is tension. So by merely looking at those directions, then that is already a variable stress. Okay, so okay, you can read about this. Consider this one. Okay, for us to evaluate, or for us to what do we call this one, understand that flexural stress, let's try to consider this beam. Okay, if that beam, for example, this is a beam, or that is a member under a certain moment on both ends. Okay, if I will try, if that is under a moment, then of course the member itself is under a bending moment, let's say M. So if I will try to cut at any section, that will be, okay, that will be under a moment M. So let's say I will try to cut at that cross section. I will try to cut at that. Then of course, for us to consider the effect of the right side, again we discussed this one on your module 4. If you are cutting a certain section, you need to consider the effect of the other side that you are removing by means of a shear or moment. But let's just focus that this is just only under moment, there is no shear. So within this beam length, that is only under pure bending. Okay, there is no shear. Okay, so that we will focus ourselves on bending stress. So if I will cut somewhere there, and then to remove this one, I need to apply the effect of that. And actually, if I will try to cut that portion and then take a moment at this section, then you will end up with a moment which is an internal moment. And again, let's forget first about the shear. So at that certain section, there is a certain moment. So if I will cut there at another section, there will be still a certain moment, which is your internal moment. And then that will be the effect of the removed part. And then that is handled, or that is being carried by the certain cross section that we are referring to, that we consider. Let's say I will cut there, and there's then that internal moment, and that will be carried by the cross section through stresses, through by means of receiving the stress, okay, due to this moment. And then that is what we are referring here as on the top as the tension and compression stress, or tensile or compression stress. It depends on the type of bending, okay, if that is opening downward or opening upward. So again, to resist, for this cross section, to resist that internal moment, that will undergo what we call as the bending stress. Okay, so that's it. You will read that one. And then of course, to relate that with the fibers that we are talking about, as I've already discussed a while ago, that the beam, which is under flexural bending or bending, will undergo bending stress, which is composed of a tension and compression. So each of those fibers there will undergo different intensities of stress. Okay, it could be compression or tension, and again the compression and tension will be divided by that boundary, which is what we call the neutral axis or the neutral surface. Okay, so that's it. If we will try, okay, now let's try to establish now or to derive the formula relating this moment M with the stresses, okay, on the cross section. So let's say again that is under that moment M, so that will bend that way. Okay, so the top is compression, the bottom is tension. So we will try to derive this in this manner, but that will be general, okay, in any type of bending. It could be positive or negative bending. So as you can see, that is originally flat, and then that will now be undergoing its deformation. So you will be having the top to be compression, below is tension. So what do we expect? Okay, originally let's say that this fiber, let's say that this is a fiber or surface, okay, surface CD, and then this below is originally parallel, which is straight, and then after deformation that will still be parallel, but they are now in a curved surface. Okay, that is now a curved surface. So what do you expect? Okay, let's say that this CD is the neutral axis. Let's say that that is the neutral axis. So even that will bend, there will be no stress. So if there is no stress, there will be no what we call as the deformation, or there is no strain. Okay, if there is no stress, there will be no strain. So there is no strain. So again, if we say there is no strain, there is no reduction of length, or there is no addition of length. Okay, there is no elongation, there is no shortening of this surface in your neutral axis. But in this part here, somewhere on the lower part, which is under tension, since that is under tension, there will be a slight elongation in each of the fiber. So let's say, let's consider a surface at a distance y from that neutral axis. Okay, let's try to consider that. That will be under tension. So if that is under tension, that will be under strain. So elongation, there will be an elongation, there will be addition length. Okay, there will be an addition, a small addition of the length. So due to elongation, since that is under tension. Okay, so if we will try now, okay, look at this. This actually surface will be forming a small part or a small arc of a circular arc, same as the other fibers here. So let's consider that the distance, okay, if that is an imaginary arc of a circle, then that will be a part of a big circle with a center at point O. Okay, so if you will try to get the radius from any of the surface, from any point of the surface up to that point O, let's say that is your radius P, or I mean rho. Okay, in the Greek letter rho. So that is your radius from that center of curvature, we call that one center of curvature, to that point here, okay, to any point in your neutral axis. Let's say that is your radius rho. And then later on, of course, to relate that one in your elongation, okay, there is again an elongation in your fiber somewhere here. Okay, so there will be an elongation. So originally that is of length up to your point E, and then because of elongation, that will elongate up to point F. Okay, that is a very, very small elongation. So let's try to magnify that one. Okay, so this is your CD, that is your rho radius, but actually this should be a circular arc. But since we are referring here to very, very small, okay, very, very small angle, okay, let's consider that AB is just a very, very small length, or that is the differential length of the beam. So if we are considering that one, then that is also a very, very small angle. So that curved surface here, we can approximate that one as just a straight line. Okay, let's approximate that one as just a straight line, since that is very, very small angle, and of course we are considering a very, very small length of the beam. So let's say now that is a triangle. Okay, we can now approximate that one as a triangle from your point O to C to D. So OCD, and that is your radius of curvature, which is your rho. Okay, and then let's consider somewhere here in this parallel surface, which is under tension, let's consider that point E and F. Okay, I will consider that is just a continuation of your radius going to your point F, okay, intersecting the parallel fiber, which is under tension. And then this here is the additional, okay? Originally, that is up to E, okay? Somewhere there, the original length of that is up to E. But because of tension or elongation or the strain, there will be an elongation additional length of EF, okay? Which is, of course, if you try to project that one and then approximate that also as a triangle or simple triangle, not a curved surface here, okay? Then we can say that if that is a very, very small angle, that is a very, very small angle, then we can now refer to this as similar triangles. So, therefore, we can now do what we call as the ratio and proportion. Okay? So, let's start with the elongation or the strain of the fiber under tension here. The elongation of that, or the additional deformation of that, the elongation itself is the EF. Okay, that is the additional length of the fiber under tension. So, let's try now to go to your strain. Strain is the ratio of the elongation over the original length. Okay, so let's say the original length of that is the same as CD. Since originally they are flat, so they have the same. If you will consider a certain cross-section or length between cross-section, the distance of the length of the fibers are the same. So, the original length of that is the same as your CD. Okay, unelongated or unstrained length, which is CD, and then the additional length is your EF, that is your elongation. So the ratio of the elongation with respect to the original length is what we call as the strain, isn't it? That is your epsilon. And then since we can apply here ratio and proportion, we can do that with your big triangle and this small triangle. So I will now be ratioing this EF over CD, okay? EF is to CD, and then now your DE, what's that? DE is to O or CO. This is your radius and then that is dy. Or this could be, you can say that this is your OD or DO is to, or the other way, FD, DF is to OD. Okay? Just apply the ratio and proportion. So what I did here is EF is to CD and then DE or what's that? DE, the small one, since that is the small part, okay? Small is to big, small is to big. So your DE, you can change that one, let's say that is Y, okay? That is actually the distance, the original parallel distance of these two fibers, the neutral axis and the fiber under tension. Okay, so that is Y, and then that is your radius of curvature rho. So you can change that DE and CO into Y over rho. Okay? Therefore, we can say that in this scenario, your strain here, okay, your strain is the ratio of Y and then your rho. Again, your Y is the distance from the neutral axis, and then the rho is the radius of curvature of the neutral axis. Okay, that we will be needing that later on to derive the relationship. Okay, so if you will now try to recall your Hooke's law, isn't it? That Hooke's law, your what we call this one, your modulus or Young's modulus of elasticity is the ratio. Okay, that is the ratio of the stress over strain. Okay, the sigma over epsilon. So if we will try to rearrange, your sigma or your stress is equal to E times epsilon, wherein the epsilon we try to derive that one as Y over rho. Okay, Y over rho. So you can change that epsilon into Y over rho. Therefore, you will have a new equation for stress, which is in terms of the distance of the fiber under consideration to the neutral axis or neutral surface, and then of course with respect to the radius of curvature of the neutral axis under deformation. Okay, so we will be using that one later on. So now if we will try to consider now the cross section, let's say that is a rectangular cross section. So this is now the cross section. I will try to cut and then look at that cross section, then that will be the case. Okay, so the top fibers are under compression, so the force are going towards the cross section, and then below is under tension, so that is going away. Okay, so by the way, the rest here from your neutral axis going to that. Okay, by the way, this is what we call neutral axis. If you are looking at this side, that is the neutral surface. Okay, but once that will intersect your cross section and that will serve as a line, we call that one the neutral axis. Okay, so above your neutral axis, everything will be under compression. Okay, but of course, the highest will be, okay, due to your formula. Look at the formula here. The stress is, okay, you can consider that your E and then rho is constant. So your only variable here is your Y, which is the distance from the neutral axis. So therefore, once your Y will be bigger, or you will try to increase your Y, your stress is also increasing. That's why this is a variable stress. So again, let's say your Y is the distance from your neutral axis going to the tension side or going to the compression side. So the bigger the Y, the bigger the compression stress or the tension stress. So that's why from 0, okay, your neutral axis is unstressed. So the stress there is 0. From 0 up to the maximum compression, and from 0 up to the maximum tension. So you can actually trace that one as a rectangular distribution of load. Okay, the distribution of load is not uniform, rather it is a rectangular from the biggest stress on the outer of the beam towards 0 to your neutral axis. Okay, so that will be a rectangular distribution of load. Okay, now let's try to consider, let's say I will consider here a fiber or just a small part of the area. So let's say that is a differential area, that is dA. So for me, I want to get the force that is handled by that fiber or that differential area. So how will I get that? Is just to multiply the area of that, okay, that small area to the stress which is that fiber under okay. So what will I be doing is multiply the stress with the area to get your force, but let's say that is a small force, so let's say that is dF. Okay, so instead of having that instead of having that stress is equal to EY over rho, I will multiply both sides by the area, okay, small area dA, to get the differential force. So multiply your stress by the differential area, you will have a differential force. Again, differential, we are referring to very small part of a quantity. Okay, since actually if you will try now to get the resultant of all this differential force which is handled by each of the fiber, then that is what we call as the resultant force that cross section is under. Okay, so now let's try to integrate both sides. So what do you expect? This will become F, and then integrate this one. Okay, you can end up there with your EY over rho times dA. You can factor out your E and rho since that is just constant. Okay, so you are integrating only Y and dA. You are just integrating their Y and dA since these are just the variable. Okay, so doing that, evidently, okay, try to read this one. Evidently, integral of Y dA is equal to 0. Okay, why? Because again, you are summating here the product of that differential area with Y of the entire cross section. Okay, so if you will do that, you will have here below a tension and on top a compression. So for the cross section to be in equilibrium, that should be equal to 0. The summation of the compression and the summation of the tension should be equal to 0. So the forces under tension, the force of tension and compression should summate to 0 to make it an equilibrium. Okay, so instead, however, in this integral represents the first moment of area. Okay, we call this one first moment of area because you are getting the moment of the area with respect to the neutral axis. So with respect to the neutral axis, since Y is measured from that axis, okay, so but from statics we may write that integral of Y dA will become your, in summating that one, so let's say I will just consider the compression side and then the tension side. Okay, so that they will not end up to 0. Let's say I will just consider the compression, or I will just consider the tension side, so that they will not end up to 0. So by summating all of that, everything below will be equal to tension, and then everything on top will be equal to compression force. But let's consider here, let's focus on the tension. So if I will try to summate that one, again, integration means summating the product of your distance and then the area of that small differential area. Okay, so if I will try to do that, then that is just the same as the entire area times the y bar, if we say y bar, that is the centroid, okay, centroid of the area multiplied to the the centroid we are referring to is the centroid of the area, and that y bar is the distance of that centroid to your neutral axis where we are taking the first moment of area. Okay, so instead of writing that integral of y dA, you can simply write there y bar and then multiply that to a, wherein your y bar, again, as I've said, is the distance of the centroid of this area to your neutral axis. And then the area is, of course, your area under that certain stress. Okay, so now if you will try to take this moment, okay, so that this one, this we are going to take the moment of that with respect to neutral axis, so that will give us a differential moment. So if I will try to take this moment of your differential force, which we derived that one a while ago as this, okay, take the moment of this differential force with respect to your neutral axis, that will be giving us, okay, that will be giving us y times df, okay, your df, you will change that one with its equivalent that we derived a while ago, and then that will just become y squared, and then again, that is now a small moment. Okay, so we are now relating, we are now considering the moment of this surface. Again, why? Because we are trying to analyze how will that surface handle the internal moment that we established a while ago, or we discussed a while ago, which is this m. If I will try to cut that, that is under an internal moment m. So that is now how this cross-section is slowly handling, or little by little handling that moment m by a small differential moment handled by each of the fiber. So if I will now try to integrate this one to get the total moment handled by all of the fibers, so I will try to do that by integrating both sides. You will have this now as your m. You will integrate that both sides, and then e and rho again are constant. Okay, so you are just integrating y squared and dA. And as I've said a while ago, okay, if your y dA is first moment of inertia, we have that y squared dA as second moment. You are getting the moment of your area twice, okay, because of that squared. And then what is that? From calculus, we call that one the second moment of area, we call that one the moment of inertia of the section. Okay, and that is also discussed in your statics. What are the moment of inertia of different cross-section, or maybe in your physics. Okay, so this is now your moment of inertia. We commonly denote that one as big letter I. Okay, so instead of writing that integral of y squared dA, since there is now your cross-section, in every cross-section shape, there is now, you can now compute the specific or the corresponding moment of inertia of that. So you can now change that. Instead of integrating, we can change that one by I, since there is now formula for each cross-section, or for each shape of cross-section. So we can now change that integral part into I. So if I will change that one, then your m is equal to ei over rho. So rearranging this one, you can have your rho. Okay, by the way, we do not care about that radius of curvature, so let me just rearrange that one and bring out that radius of curvature rho. And then previously, isn't it, from a while ago, we derived that your stress is Ey over rho, isn't it? We derived that one a while ago. That is what the first relationship that we derived. So bringing out here again your rho, this will be rho is equal to Ey over the sigma, the stress. And then now, for us to eliminate that rho, let's try to equate these two equations. Rho is equal to rho, so you will end up here with Ei over m is equal to Ey over sigma. And then you have the E and E, your Young's modulus will cancel each other. So now you are left with I over m, y over sigma, and then rearranging, you will have your sigma is equal to my over I. So what does that mean? What is sigma again? That is the stress. So if you want to get the stress experienced by that fiber, then all you need to do is divide that moment by your, or multiply the moment by the ratio of the distance of that fiber. Okay, y is the distance of the fiber under consideration from the neutral axis, whether that is a compression or tension. Okay, y is the distance from the neutral axis, and then I is the moment of inertia of the entire section. So just multiplying this ratio to your entire moment. Again, your M is the entire moment handled by that cross section. Okay, that is the entire internal moment. This is now the internal moment at that cross section. So we will have to distribute. All we need to do is distribute this M, this entire internal moment, in each of the fiber, and then each fiber will undergo a stress which is equivalent to the ratio of Y times or Y over I. Multiply that one to the entire moment. You will have the stress which is to be handled by that fiber, specific fiber. So if you will now try to summate all of these stresses, then that will be the one handling the total internal moment M. Okay, so that is now the relationship of the internal moment with the stresses on each of the fiber. And as I've said, if you try to look at the formula, the stress, okay, let's say M is constant and I is constant since we are referring to a single cross section, but your variable here is Y. So as your Y, okay, as you consider different fibers here in your cross section, your Y is changing, therefore your stresses are also changing. So we call this one again variable stress. So moving on, so if you'll try to look at this again, that is just described here. I already mentioned that one a while ago. So if you want now to get the maximum stress, let's say you want to get the maximum compression stress and then maximum tensile stress, again as I've said, your Y is directly proportional to your stress. So as your Y increases, your stress increases. So where will we find that biggest or that maximum tensile and then maximum compression? You will find that one on the extreme fiber or on the outer surface of your cross section. So for us to get now your maximum, okay, for us to get the maximum value of the stress, okay, let's put there sigma sub max to indicate the maximum. It's either compression or tension, okay. If you are considering here the tension part, then that is the maximum tension. If you are considering the compression part, then that is a maximum compression. So that distance Y will become the distance from the neutral axis to the outermost, and we commonly denote that one as your C, okay, centroidal distance from the extreme surfaces. So we denote that one as C. If that is a rectangular, your C, your neutral axis is found exactly on the centroid at the middle. So your distance from neutral axis to this extreme upper part and then the lower upper part is the same. So you can just divide the height into 2. That is the value of your C. But of course, later on, if you will end up with another type of cross section, let's say rectangular, triangular, circular, trapezoidal, or I shape, then the C will be different. Okay, it depends. So for simplicity again, if that is rectangular, or if that is any section, that C there is the distance from the centroid or from the neutral axis to the outermost part, okay, which is under tension or compression. So that is now the relationship of your stress and the internal moment, and then of course within your cross section. So again, if we will try to recall, we assume that the moment, internal moment that will bend your beam concaving upward is a positive bending moment. And of course, we try to prove that one in drawing your, or we use that one in drawing your shear and moment diagram or your moment diagram. Okay, a positive moment, and if you try to draw the deformed shape of that, the positive moment corresponds to a curvature of beam opening upward, and then the negative corresponds to concavity, which is opening downwards. Okay, so that is what we will be following. So for example, look at this. For this beam, we had this one in your examples in your module 4. This is now the moment, okay, but of course for you to draw that one, you need to pass your, you can draw if you can take a moment at any sections and you can draw directly your moment diagram, no problem, you do not need to pass your shear. But if you want, or if you still cannot do this directly, then you should pass with your shear and moment, shear diagram. So this is the moment diagram of our previous examples before, okay, these are the moment diagrams. Now again, if that is a positive moment, then this entire beam is opening upwards, which is true since that is the type of loading. So that will only bend, okay, opening upward, since again you have here positive moments. And then here, negative moment. So therefore, that means that your entire beam will concave downward. So this is your deformed shape. Okay. So negative moments. So again, if you will try to go here, if your positive moment or bending moment, if the section is under positive bending moment, what happens is that if that is concaving upward, your upper fibers are compression, your lower are tension. If that is a negative bending, your upper is tension, your lower is compression. So that means in this beam, the entire fibers from A to E on the top is under compression and below is under tension. This is the opposite of this example. The entire fiber on the upper part, since this is concaving downwards, is under tension from A to D and below is compression. Okay, so that is how we will relate your stresses, okay, the type of stresses of the fibers, okay, with respect or relating that one with your moments or your moment diagram. Okay, so this is the simplest way to outline the entire beam. Okay, instead of cutting and then and then of course take noting of all the values, so it is better for us to outline that one using the diagram. Okay, so look at this. In this example, we have this one also. These are our previous examples. This is the moment diagram, so that will be entirely, okay, opening upward. So compression on the top, tension below. But in here, look at this. We have a negative, we have a positive moment. So that means, okay, these negative moments will have our beam opening downward. And then at that point, okay, we have this one. This is your example number 4. Say example number 4 in your module 4. We have that point of zero moment. That is where the change of curvature will happen. And I discussed that one also. Okay. So from that point of inflection, okay, this is opening downward, and then on the other side, it will now be opening upward. Okay, because your moment is positive. So on top is compression, below is tension. In here, below is compression, on top is tension. So we have a reversal of stresses. Okay, even if that is now a single fiber, you are considering a single fiber from the entire length from A to D, and in this length that is under, okay, we are considering, let's say, a top fiber. So in this length from A to that point of zero moment, that is under tension, but as that goes on the other side, it will now be under compression due to this type of loading. Okay, so bending in relation to flexural stress, again, that's it. This is just what I discussed. Okay, so again, compression, tension. So this is just the outline of that. So let's try to have here an example. Okay, so consider the given loaded beam below, determine the maximum flexural stress, and then the maximum flexural stress, which is tension, and then the compression. Okay, so look at this. Okay, this is the beam. Draw, of course, first and foremost, draw the moment diagram. That is where we will be getting the idea, okay, which one is under tension and compression. And it says there we are going to find the maximum tension, tensile stress, and then compression, compressive stress. So where will I find that? Look at the formula again. This is your formula. The stress is just a part, okay, the stress on a certain fiber is just a part of the moment, okay, just a small part of the moment. Therefore, your stress will depend on the moment. So to get the maximum tensile and compressive stress, we need to use the maximum moment. So I need to find there the maximum moment. So you cannot just find that one by merely looking at the loaded beam. You need to draw the moment diagram. Okay. For starters, you need to draw the moment diagram. But if you are already well versed with this, you can actually find out by using the equations. You can find out the maximum moment. And actually, on your higher subjects, you have already a ready formula for a certain type of loading for the maximum moment. Okay. So, but for us, let's start by drawing the moment diagram. So this is the moment diagram. Where is the maximum moment? You can find it here. Okay. So therefore, we are finding the maximum tension. If that is a positive moment, you can find the tension below. So if this is the cross section, you can find the maximum tensile here, and then the maximum compression here on the fibers located on the extreme parts. This is your neutral axis. By the way, neutral axis is located on the most, since we are referring to simply loaded or simple beam bending, okay, we are not on the advanced beams, discussion of beams. So we are considering that considering a simply loaded beam, so that is under simple bending. So your neutral axis passes on the centroid. So the centroid of this rectangular is found at the middle. So therefore, your neutral axis here is actually just half of the height, which is 200 going down, 200 going up. Okay. So again, let's continue. Okay, that is, of course, you can read about this. I already explained that one. For us to get the maximum stresses, you need to use the maximum moment, and that is here 26 here. So that is your maximum moment. So again, as I've said, this will be under compression, that is under tension, due to this type of concavity. And of course, you can read that one by understanding the value or the sign of the moment. Okay, so if that is your moment, 26, okay, kilonewton meter, positive. And then again, as I've said, this is a simple rectangle, so your y bar or your NA is located at the centroid, which is on half of the height. So 200 down, 200 on top. Okay, so the distance for tension, the C for tension is 200. Again, we are getting, by the way, we are getting the maximum tensile and maximum compression. So you will find that one on the farthest distance from the neutral axis. I already discussed that one. The bigger the Y, the bigger the stress. So the maximum is found on the extreme fibers. So for me to get this extreme fiber, my distance C in compression should be 200, and my distance C for tension is also 200. So that is what I will be substituting for our formula. Stress is equal to MC over I. Your I here, by the way, this is discussed in your statics, okay? From your statics, this I, okay, this I for rectangular is 1 over 12b h cubed, okay? This formula, by the way, is the inertia with respect, or moment of inertia with respect to the neutral axis. If you want to get the moment of inertia with respect to other axis, that will be different, okay? So this formula, which is derived from your statics or your physics, is actually with respect to the neutral axis. So the moment of areas are done on the neutral axis. Okay, so 1 over 12b h cubed. Your b there is the width, and then your h there is the height. So substitute that one, you will have the I with respect to the neutral axis as 1.333 times 10 raised to 9. Okay, that is rounded. Millimeter 4. So moment of inertia is millimeter 4. Okay, and then stress there, we can now start with the maximum tension. So let's say max, I will put there sub T to differentiate that with your maximum compression. So what is the C? Okay, what will just be the difference here is the distance, if that is for tension and compression. However, in this example, Y for or C for compression is the same as C for tension. So we will have the same value for sigma for tension and compression, but the other one is tension, the other one is compression. So that is how you will do it. This is your M. Make that Newton millimeter, so that you will end up with, everything will be Newton millimeter, so that you will end up with megapascal. So Newton millimeter and millimeter divided by millimeter 4, millimeter squared and cancel with the squared on top, you are left with Newton per millimeter squared, which is a megapascal. So 3.90, that is rounded. Okay, so that is the maximum tensile which is experienced by extreme fiber below, which is found within this section at joint D or at section D. And then the maximum compression is also found at this extreme fiber on top, which is also found at section D. Okay, so that is for this example. Again, your stress is equal to MC over I. Let's have one more, okay, but this time we will now be having a built-up section or I section, which is, it is symmetrical with respect to a vertical, but it is not symmetrical with respect to the neutral axis. So the challenge here is that your C values on the top and then the below are different, since of course by merely looking at these areas, it is not symmetrical with respect to the neutral axis. So This is what we need first to establish. Okay. But first, of course, we need to draw the moment diagram. So again, since we did this one before, this is the moment diagram. So you have here 2. Okay. It doesn't always mean, okay, that since that is a bigger number compared to this, that will give us bigger or maximum stress. As you can see, okay, that is true. Okay, this will be true. You can say that will give us a maximum stress compared to this if your cross section is symmetrical in both directions, just like a rectangular shape. But in here, look at this. This is unsymmetrical. So in this one is a negative. It means that this below will be under compression, isn't it? And that will be under tension. But once we will go here on this maximum 40, that is now the reverse. Compression on top and tension below. And actually you cannot decide which one will give us the biggest or the maximum stress because the Y will be different. The top here, let's say, if you want to get the maximum tensile stress, the tensile is found on top. On your -9, you will find that one on top. The tensile on your 40, you will find that below. So your values of Y will be different. A while ago, your C is on top, but this time, if you will go here, your C is below. So by merely looking at this figure, the values of C are different. So we cannot say that your stress is bigger in this 40 compared to 90. So I will solve that one. We need to solve this both. Okay? Since there's a reversal of stress. So to do that, okay, again, you need to put in mind that the maximum is found on the extreme fibers. So that is first what we need to find out, where the neutral axis is located. Okay. That's it. Where we will find the neutral axis. Okay, so first is to find or locate that neutral axis. So from your statics again, finding your centroid, okay, using this theorem, the summation of the moment of each area with respect to an axis. Okay, let's try to get that moment with respect to the bottom part. Okay, so summation of the moment of each area. So let me divide this section into areas. Let's say this is the area 1, area 2, and then area 3. Try to take the moment of that with respect to the base. And then that should be equal to, if you will try to cross multiply this one, that should be equal, if I am summating that moment of areas with respect to this base, that should be equal to the moment of the entire area with respect or multiplied to the distance. Let's say that is Y bar. Distance of the centroid of the entire. Okay. The neutral axis again is found on the centroid. So that Y bar is the distance of the centroid from the base. So to do that, I need to calculate the area. So better to tabulate that one. It will be helpful. Okay. Or you can do it directly using the formula, of course. So area, to get the area of 1 is 60 times the height, 20. So that will give us 120. Area for your number 2 is, the thickness of that is 10, and then the height is 80. So 80. This should be, 80, this should be 8. This is just a typo. Okay, so that is just a typo. This is 60 times 20 is 1200, and that is 800. So area for this is 80 times 10 is 800. This is 100 times 20 is 2000. Okay, and then summate that one, that is the total area, which is 4000. And then of course the distances of those area. Okay, get the centroid of this. Those are just rectangles, so the centroid are found at the middle. So centroid is the center to this base. Okay, since we are getting the moment at the base, or the product of the area and the distance with respect to the base. So distance of that is 20 plus 80. Okay, 20 plus 80 plus half of the 20 will be 110. The distance for your area 2 to your bottom, okay, the center of that is 20 plus half of 80 will be 60. And then this last third area is half of 20 is 10. So these are our values for Y, and that is for area. Substitute it here. Summate the product of area times distance, and divide that one by the total area. You will end up with 50, which is the centroid of the entire area. Okay, the total area. So that Y bar here is 50, and that will be our C later on for the, if this is under tension or compression, that will be our C, since that is the outside or the outermost, outermost fiber. And then on top, okay, the C will be, all we need to do is subtract. What is the total? 20, 80, and 20 will give us 120. Subtract your 50. The upper C will be 70. Okay, so that is what we will be needing later on. But, of course, we need to calculate your inertia, since this is not simply rectangle. It is a built-up of rectangles. So, recall again from your statics that the inertia of a composite, okay, inertia of a composite member is the summation of the I of each of these rectangles or each of the areas plus the area multiplied to the distance D. Your D is the distance of the centroid of each of the area to the neutral axis. So we need to calculate the distance. Since we know the area, your I, these are just rectangles. So again, that is 1 over 12 base times height raised to 3. Okay, since for that is a rectangle. But we need to evaluate your D or find this D in each of the area. So for D, from the neutral axis of your first area, okay, so our neutral axis, the distance to the top is 70, isn't it? Okay, so 70. And then, by the way, that distance here, this is 110 from the base. Maybe that is what we need. That will be the one for us to be, that is what we'll be using to solve, okay? So from this base to that centroid is 110. So all we need to do is subtract your y bar to get the distance from the neutral axis. It will give us 60. And then from that centroid of this second square to that base is 60. Subtract your centroid, the distance to the neutral axis 50. That will give us a distance from NA to the centroid of that to be 10. And then lastly, here below, of course, your C is big. I mean, your centroidal distance is bigger than that one. So I will be than this from the base. So I will now be subtracting from your y bar, which is 50, the distance of the centroid to the base, which is 10. So from the centroid to that neutral axis will be 40. So now all we need to do is apply this one, summate in each of the area. So first, again, base height cube over 12, that is the I for a simple rectangle with respect to the neutral axis. But since again that is with respect to the neutral axis of each area, we call that one the centroidal or the moment of inertia, centroidal moment of inertia. But now we will transfer that one. We call this one the transferred moment of inertia. We need to add that AD squared. Okay? So BH cube over 12. So your B is 60. Your H is 20 cube over 12 plus 120, that is the area. I'm sorry, that is not 120. Let me just change that one again. That is just a typo. Okay, so again, that is typo error. Okay, so we changed that one a while ago. We forgot to change this one. So when I change this one, that is just following your transferred moment of inertia formula. Okay, so if I will now use this one again, BH cube over 12. Do not forget to add your AD squared since we transfer the moment of inertia with respect to your entire NA. This BH cube over 12 is only with respect to each of their neutral axis. Okay, so do that one in each of the area. Okay, see BH cube over 12 of this first plus AD. Okay, this is your area D squared, and then second is base is 10 times height is cube is 80 is cubed over 12 divided by 12 plus 80. That is the area times 10 squared. Okay, same thing in your third area. 100 times 20 cube over 12 plus 2000 area times your 40 squared. Okay, so that will give us an entire moment of inertia for the entire section of 8.133 times 10 raised to 6 millimeter raised to 4. Okay, so that is the I that we will be using. So we need to investigate again the maximum negative moment and the maximum positive moment. Okay, so again, these are your values for this. By the way, this C on top is 70 and C below, we solve that one to be 50. So for the section in your negative 90, below is under compression. So, okay, since that will curve downward, so this is under compression, so we will be using there a C of 50 and on top is a C of 70. And then on this one, section of the maximum positive, which is 40, that will be reversed. Your C on the tension is 50, your C for this tension is 50, your C for the compression on top is 70. Okay. So now all we need to do is input on the formulas. So again, your sigma is mc over I. So m for let's investigate first the positive moment 40. So mc over I, that will give us 245.91 megapascal. That is your tension. On top is tension, okay, and below will be on below is tension, on top is compression. Okay, so that is the top, which is 50, below, which is 50. So that is tension. On top, all we need to do is change the C to 70 to get your compression, which is 344.28. Now we need to compare that one with the value. If I will make your negative 9 the maximum or the moment, okay, so change that one to 9, your moment to 9, okay, convert that one of course always to Newton millimeter so that we will go directly to megapascal. So your C on the tension, your tension now is the top. So your C is 70. That will give us 77.46, and then below that is compression will be 50, so 55.33. If I will compare the values, okay, so these are now the values. What will be the maximum tension is from the positive moment 40, so that will be your maximum tension. And then your compression, compare that one, is still your maximum compression is from your positive 40. And again, there are some cases, since this is actually very far, if this will be a little bit closer to that, maybe we do not know, because again your C are different. If this is just a rectangular, your C are equal, you can say that this will be giving us the biggest or the maximum, but we cannot decide that right away since your C are different. So we need to compare the values of the maximum negative and the maximum positive, and this is what happens. Look at this again. You need to bear this one in mind. In a negative, your top is tension, your below is compression. In a positive, your top is compression, below is tension. So you really need to evaluate the stresses of each of the maximum, negative, and positive before comparing which one will be giving us. So that's it. That is for the answer for this example number 2. Okay, so if you have any question regarding your bending stress, okay, or yes, the bending stress of beams, then we can discuss that one. You can comment that below the video, or we can discuss that one on the live meeting. So thank you very much for watching.